this AP skier question there at the back of your packet. A skier has a mass m and is skiing down a frictionless hill that makes an angle theta with the horizontal, as shown in the diagram. The skier starts from rest at t equals 0 and is subject to a velocity-dependent drag force due to air resistance. So that air resistance force is equal to BV, opposite the direction of the velocity, where V is the velocity of the skier and B is a positive constant. Express all my algebraic answers in terms of the mass of the skier, m, b, theta, and other fundamental constants, so like the acceleration of gravity, g. Part A says, on the dot below, draw a free body diagram indicating and labeling all the forces acting on the skier. Okay, so let's put a dot on here and we'll draw what forces are acting on our skiers. So we definitely have gravity, mg, acting straight down, a normal force perpendicular to the surface, and then that drag force F, pointing opposite the direction of the motion. So there's my part A done. That was kind of nice. Part B says, write a differential equation that can be used to solve for velocity of a skier as a function of time. Okay, so the key wording here, a differential equation for velocity. So I know when I read differential equation for velocity, they're really looking for something that has dv dt in it. Well, I know dv dt is the acceleration. So I need to basically write an equation that has acceleration in it and then substitute in dv dt. So what forces are acting on my skier? Because I know if I add up the forces in the x direction, I'm going to get ma. There's that a that I can substitute in my dv dt. I'm going to rotate my coordinate system so that my acceleration is only in one direction. Therefore, I only have one equation. In doing so, I will need to go ahead and resolve this mg into components. Just for safety, I'm probably not going to draw this on the free body diagram I drew previously in part A. I'll probably draw it in a separate location so it doesn't mix up the grader at all. So I have mg sine of theta, where this is theta because this is theta. And then I have mg cosine of theta here. So in my x direction, I have mg sine theta, and then I also have my resistive force acting the opposite direction equal to bv, m times a. And I'm going to replace a with dv dt. I now have written a equation, a differential equation that could be solved for velocity. Now they didn't use the word derive here, they just said write. If they did write derive, I would have to show this. I would also have to maybe say minus the f and then say that f is equal to bv, something along those lines if they had done the derive. Okay, part C says determine an expression for the terminal velocity of the skier. Okay. So terminal velocity, Vt, is when acceleration equals 0. So basically I'm solving for the V when the acceleration is 0. So I can say then that mg sine theta equals bvt. So my acceleration was 0. Key to write that out. They're probably going to give me points just for saying that acceleration equals 0 in this scenario. So now I know that my terminal velocity is going to be mg sine theta divided by b. And I should check every time I write out these equations that I am meeting that criteria, that I'm putting it in terms of m, theta, and b. So, and other fundamental constants. Yes, m, theta, b, v, because it's a differential equation for velocity, it's okay that I have velocity and dv dt in there, and then m. Okay. Part C, now it's going to, part D. Now it's going to get difficult. Solve the differential equation. Okay, so the reason it gets difficult here is simply the algebra and the calculus involved. So I'm going to show you kind of the way I like to do it. You don't have to make the substitution for Vt. I usually do because it makes it a little quicker, and then I'll substitute the mg sine theta divided by b back in at the end so that I meet that criteria on what it's in terms of, because it definitely should not be written in terms of Vt. All right, So the first step is I want to get a VT. So that means I'm going to divide everything by B. So now I have mg sine theta divided by B minus V equals m over B dV dt. Okay. So this term turns to VT. Okay. So now I have VT minus V equals m over B dV dt. So now I have my V over here that I have to get with the dV over here. So I'm going to move the B and the m over to this side. So I'm going to multiply by the reciprocal. I'm also going to multiply the dt over, and then I'm going to divide the VT minus V over to the other side. And so now I have B over m dt equals 1 divided by VT minus V dV. At this point, we can integrate. And so I'm going to integrate with respect from 0 to t, and my initial velocity at 0 was 0 to my final velocity v. I'm choosing to do a definite integral as opposed to doing the plus c's, just because it's a little easier in my opinion. Okay. Next, you can do a u substitution. So I'm going to say u is equal to vt minus v. So then du is equal to negative dv. Okay, so we make our substitution. So over here I have bt over m. On this side I have 1, well I have a negative, 1 divided by u du. There I'm seeing my natural log function pop out. I am going to move this negative sign over to the other side as well. This is a thing that makes it a lot easier, but can easily be missed. Okay, so I have negative bt over m is equal to, and now I have the natural log of vt minus v evaluated from 0 to v. Putting this together, I end up with the natural log of vt minus v minus the natural log of just vt. So in subtracting natural logs, I can actually divide those. So now I have negative bt over m is equal to the natural log of vt minus v divided by, oh, careful there, don't need that far, divided by vt. Okay, so now I'm going to go ahead and get rid of that natural log. So let's kind of move up over here. So now I have e to the negative bt over m is equal to vt minus v divided by vt. Multiply my vt over, e to the negative bt over m. And part of the reason why I made that substitution for vt is when I'm moving things around with these vt's, it's a lot easier to write vt than all of that. Okay, so I'm going to move the v over, I'm going to move this term over there, so now I have it v equals, and so I have vt times 1 minus e to the negative bt over m. So I move this term over, factored out of vt. Okay. And now the last step, I need to go ahead and substitute that back in. So I have v is equal to mg sine theta divided by b, all times 1 minus e to the negative bt over m. So a lot of the difficulty on this is quite a bit of like math work to get this answer. And so that's where the difficulty comes on that one. And then lastly, e, on the axis below, sketch a graph of the acceleration function. Okay, so now I want to see, what does my acceleration look like? So what happens to this term as time goes on? So you can imagine that if I substitute all of this in here for v, now I have an acceleration function that's dependent on time. And if I plug in 0 for time, I get 1 here. E to the 0 is 1. 1 minus 1 is 0. So this term, the velocity term, is 0. Well, go figure, right, at time 0. So this term all goes to 0. So I know that my acceleration starts out as mg sine theta. Okay, so the idea is when I make my little sketch, I have mg sine theta. That's where it's going to start. And I do have this e to the negative power. So I know that as time goes on, this is going to approach 0. And so I'll say that a approaches 0 as time approaches infinity. Just to make it clear that there is an asymptote there, in case the grader can't quite figure that out from what I've drawn. There you go.